All right, so I don't know what's your favorite part about this class, but for me, like the lecture today is definitely part of my favorite part of the class. So today we are going to talk about programming on modern processors, and we are going to talk about the single-threaded version. And as you can imagine, later on we are going to have a multi-threaded version. But before we talk about that, let's remind ourselves what's a modern processor look like. So if you could have remembered, we said every modern processor is not like the 5-stage pipeline in your textbook. Instead, it's a multi-functional unit pipeline like I draw in this figure. And in addition, there are also features that would allow us to reorder the instruction dynamically. However, when we commit finishing those instructions, they are back in order so that we can always ensure the correctness of our program. So what does that mean is that we are basically scheduling instructions on their data dependencies. However, if through a very naive design, we are limited by the issue width of the hardware, also the fetch width of the hardware. So later on, we talk about modern processors are typically so-called superscalar processor. And the point of superscalar is that instead of just issue one instruction, fetch one instruction at a time, we are able to issue multiple instructions and fetch multiple instructions at the same time. So this applies to most modern processors like the Intel Alder Lake processor. It's a 12-issue processor. And so it turns out modern processors, they all have these features that they are capable of issuing multiple instructions at the same time, which means that if you want to write a program that could be outperforming than others, what you really need to do is that can we leverage those concurrently? And modern processors, they all have caches in a way that if your code can exploit the locality, then it's definitely going to perform better. And finally, we also have branch predictors, which means that if you can make your code more predictable, more regular, it's possible that you are going to get better performance. So, and the reason why I'm saying that is that, well, simply the hardware innovation is not enough, right? So through the data flow analysis in scheduling a linked list-based code, as you can see from this data flow graph, no matter, so for this data flow graph, we draw the data flow graph based on the assumption that we have unlimited fetch bandwidth, fetch issue width, which means that even though I give you good enough amount of functional units, if you are running code like linked list, it's impossible for this code to be performing anyway, no matter how good a processor you have, just simply because the code itself has too many data dependencies. So if your code is unable to exploit multiple functional units efficiently, even though you have the best processor, it's going to be underperforming. So in this lecture, we are going to talk about how can we so last time we were talking about, okay, instead of using linked list, we should try to exploit other data structures like array to make our code more efficient. And today we are going to walk through one more example to demonstrate how to exploit more parallelism from the code that is given. So this is the problem we are going to talk about today. So this problem is called pop count. So pop count its full name is population count. It's a problem that if I give you an integer, please count how many bits within that integer is 1. And you might think about, oh, why is it important? So in fact, it's super important. If you ever learn computer networking or any kind of channel coding, we all have this like error correction code or checksum, which we want to know if any bits that's being transferred over the network or over any median is wrong or not. So the simple way to do this is that we just check the number of ones or zeros within the encoded content to see if that fulfill another checksum that we sent attached with this data segment to see if there's any correction needs to be done. Should we ask the sender to resend the data? And so that's one of the things that people would typically do. Compression algorithm, for example, like based on how many ones or zeros, we may have different lookup tables for the compression result. That is also using this pop count. And like sparse matches multiplication to figure out where are the ones, where are the zeros. That's also that's also an application of this. And like fingerprinting or a lot of data structures that use big vectors, they all need this pop count. So what is pop count? So if we use a LeetCode format to describe this question, it's simply like this. So for example, if I give you an input number, and this is the binary representation of this input number. Tell me how many bits in this number is 1. So for like this number, after encoding to binary, we know its output is 1. So if you want to write a code, so basically, if it's a LeetCode problem, right, we would ask you to write this pop count function given a random number inputs, and we want to so that's the code that we're dealing with. So now I have 5 different implementations. Looking into this 5, can you tell me which would perform the best on modern processors? All right, so now let's take a look. All right, so this is the diverse answer that we have seen. So why don't you guys grab a few people around you and let's discuss which would be likely the answer. All right, let's take a look. Okay, this is what we got for after the discussion. So most of you now think the answer is D. So can I have someone explaining why you think D is the right answer? Like, why do you pick D? Because it looks most counterintuitive. Any insights? Any idea? Why you guys pick D? What do you have?
I was thinking either between C, D, or E, and D was like one of the best options. I didn't think A or B because it looks like X is being used a lot.
Hmm.
So there might be a lot of dependencies with that.
Okay.
With A and B.
Okay, so if we want to rank, now you guys rank D is the best. And who is the second?
C, because C is basically
C is the second? Why?
because I think the only difference is
Is a while loop? So why is having a while loop not doing better than D?
I'm not sure. I couldn't decide between this.
It has to do with like how earlier example was a link list and we use a Y because it's like that.
But do we, okay, so you think the X creates a data dependency?
Yeah.
Okay, then why do you think C is better than B?
I think one of my person that I talked with said that C would be able to utilize like a multi-processor, multi-issues.
We don't have multiprocessor in a context now,
Okay.
right? Because I think we said it's a single threaded version, right? Right. So why do you think, then how about A? Is it better than B? No, why not? Okay, because it used loop unrolling. Now you guys learn loop unrolling. But why C is better than B? Anyway, let's run a demo first, right? But the answer is indeed D, right? But let's take a look. Like, what's their performance difference? So this is the problem. This is the code, exactly like what I provided. And let me run this. And we have different versions of the code. And now let me run, like this is the version E. And now let's run it, who has the best performance. Now let's run the code and see what's going on there. Okay, so now let's take a look for version A. We are running it, and this is an Intel 13th generation processor, and which is not too bad. It still sells for $300 on Amazon, so it's a pretty decent processor. However, okay, so for version A, it takes 22 seconds to finish it, right? So that's the baseline right now, right? Because we have the first, and this is the most simple, naive way you can think about how to write a pep count. And with version B, it takes 12 seconds, right? Which is almost twice as fast. And now I'll not even finish what I'm talking about. Version C give us the answer for 5 seconds. However, for version D, it does even faster than version C in a way that it only takes 3.7 seconds, right? So if you are a software engineer, a lot of people would tell you, well, try to write a case switch statement, right? That's easier to interpret, right? You must feel that way, right? So like version A takes 22 seconds, version B takes 12 seconds. Let's see like how much time version A would take. And I'm sure it's already more than 22 seconds, right? So version A is not only not like faster than others, than version D, is indeed probably the slowest. And how slow it is, right? So I'm running out of words and I still don't get an answer from E, right? Is it the code finishing? I'm going to show you. It's going to finish, but not with a very good performance, right? Yeah, just like, oh, all right, 1 minute and 11 seconds, right? So it's 72 seconds, 71 seconds, right? So which is almost like 3.5 times longer than the A, right? So this is definitely not good. So today in the lecture, we are going to use this 5 different versions of the code to tell you what IOP plays in there and what tricks does the programmer use to make the code has different performance. So let's take a look at version B and A. Can you reduce the sample? It's not working? Okay. Now, why don't you guys discuss with each other and vote again? I guess the problem is gone for some reason. All right, let's take a look. So after discussion, C and D. Okay, so what is C and D? Let's take a look. So C is, so C and D, 2 and 3. Okay, so let's take a look. How about the A, the first one? Is B going to have lower dynamic instruction count than A? No? Why? It has more lines of code, but for this lines of code, how many iterations it represents? 4, right? So for dynamic instruction count, right? So all you need to do is like this 2 statements plus 1 branch, right? But here is 2 statements. So this 8 statements plus 1 branch for every 4 iteration, right? So to be short, you can imagine for this pieces of code, it's pretty much like, okay, 2.25 per iteration, right? But this is pretty much like 3 per iteration. Agree? Right? So if we say the statement is related to instruction count, then this gives you a rough ratio for that, right? So it's probably reasonable to say that, right? How about the second one? Or maybe we can look at the third one. Do you guys agree with that or not? Yes or no? Yes or no? For the third one, are we going to have fewer branch instructions or more?
Fewer.
Why is fewer?
Because there's more steps that happen between branches. So like we're getting less. We're gonna branch less.
Okay, so another way to think about this, right? So for the left-hand side, you do a branch every iteration, right? Every 2 statements, right? But here, you only do one branch every 8, right? And this 8 is equivalent to 4 here, 4 iterations here, right? So another way, right, we can interpret that in this way. Every iteration here needs a branch instruction. Here, because we combine an iteration, 4 iterations into just one loop iteration here. So we only need one branch every 4 iterations, right? So the amount of branch is significantly reduced. But how about the misprediction rate? Why? So what's the prediction rate about? The accuracy of predicting a branch, right? But there must be a case we always mispredict. What is that? For this pieces of code. Thinking about like you have a 64-bit number, right? And we are going to, so this is while x, right? So whenever the x is a non-zero value, zero value, we are going to branch out, right? But when the number is going to be 0, that's kind of like unpredictable, right? So we are always going to mispredict at the very end, right? However, if you're always going to have one misprediction and you have fewer number of prediction to make, who would have higher misprediction rate? Actually, B's misprediction rate is probably going to be higher. However, because we have fewer branches, right? So maybe the performance will be better. But how about a CPI? Who would have better CPI? B. Why? Less branch instructions. And as we said, the branch instruction may not be that good if, well, less branch instructions, but if we have higher misprediction rate of the branch, how can a CPI be smaller, right? So this is kind of like an unknown. So let's run. Question?
Could you explain number 1 again? Why the instruction count?
Okay, so I will explain that later. But at this moment, let's run the real performance stats to see what's going on. So right now, I'm going to run these 2 versions. And as you can see, let's take a look. Instruction B, version B, the instruction count is indeed fewer, right? And the number of cycles is a lot better. The CPI, cycles per instruction, is also better. Execution time is shorter. The data cache miss rate is about the same. Let's take a look. Okay, so here is the branch misprediction rate. So this one, okay, surprisingly, is lower. And the reason why it's lower is actually kind of because, and if you check the number of branches it eliminates, right, it's actually like 1/4 ratio as well, right? So one hunch I have is because the randomly generated number and because we take, because the randomly generated number probably is sparse enough in a way that like it always ends at the very end. So you still have a pretty good branch prediction. And the other thing is that probably the randomized function itself is also not too random in a way that the processor could capture that, right? But if you take a look of the profiling result, right? What we will find is that among the statements, right, first, the branch has lower than A instruction count than A. That's true. And the reason, like you ask, right, is because if you look at that, this is version A, this is version B. So for version A, if you compile it, it will need 5 instructions to implement this iteration. And for the version B, if you compile it, it seems like this iteration would need more instructions. However, don't forget, every iteration here is equivalent to 4 iterations right here. So if you have n iterations to perform, version A would take 5 times n. But for this one, it would be 17 instructions multiplied by n divided by 4. So on average, it would take about like 4.25 times n number of instructions, right? So that's why the instruction count is lower. Okay. Now let's take a look why the CPI of B is better than A. And the answer is kind of like unrelated to branch. So why is that? So let's take a look, right? So this is a data flow graph, data dependency graph that I draw from A. And here I assume we have unlimited fetch issue bandwidth. I have like 100% correct branch prediction and 100% correct cache. However, this piece of the code has no memory access, so there's nothing to do with the cache. However, if you draw the data dependency graph, you will see there's always a data dependency between 1, 2, 3, 4, 5. So that's the data dependency graph you will draw, right? And now, for each iteration here, right? Each iteration here covers 4 iterations. If you draw a data dependency graph with the latency being considered, each iteration here basically would take 1, 2, 3, 4, 5, 7 cycles. It seems to be longer, right? But now let's keep unrolling this graph. So saying that I have another iteration. Then when I unroll this data flow graph, right, you will figure out the total end-to-end latency only adds up 1 per iteration, right? So with that, you can kind of like conclude the number of cycles that we need for A is depending on how many iterations you have. If you have n iterations, it would take roughly n cycles to complete the operation. And this is assuming you have perfect cache, perfect branch prediction, and unlimited fetch issue width, right? So that means that the best case is that 1 cycle per iteration, right? Now, if you unroll this, right, you will figure out that, oh, wow. So for this set of instructions, right, it takes, oh, shoot, critical path, 2 cycles per iteration. Why is it 2? For some reason, I counted as 2. 2 cycles per iteration. So for this one, I need 4 more cycles for every 4, right? So this is like 1 cycle per iteration. And this, why do I put 2 here? So for this, let me see, why is it 2? So for the 3, for the 4, why is it 2? X, ECX, NL, NL. Okay, so I can double check with that. But from this, it will tell you basically, if you consider the number of instructions it has to perform and the number, and you only need 4 cycles for this every 4 iterations for this giant amount of instructions. So its CPI is actually going to be slightly better, and given you have smaller instruction count, that's why B is better than A, right? but I will double check with that. Now, so if you check that, right, these are the correct ones. And through our profiling, 2 is also correct, right? But intuitively, at least, you have to find out 3 things that's correct. Okay, so the second thing, the second tips in programming on modern processors is that loop unrolling is effective as control overhead is still significant, even though we have branch predictors and auto order execution. Now, why is C better than B? All right, let's take a look. So, it looks like a lot of you picked C. So why don't we discuss on why you think it's C? All right, let's take a look. Okay, after discussion, more of you think the answer is C. So before we talk about what are the 2, can you guys tell me what are the 2 that you have in mind? How about the first one? Lower dynamic instruction count? Why? What? Okay, so right now, previously we are doing 1, 2, 3, 4, right? So we do it one by one. So it sounds like okay, we have combined those 4 instructions into 1. Okay, so significantly reduction. What else? How about this? C equal plus. So high levelly, what's the difference between version C and B?
You combine all of the operations into the table.
Okay, So this is actually a table, right? So it tells you if I and, so if, okay, so it's basically telling you, right? If right now the segment that I'm looking at, if it's equivalent to 0, then there's no ones, right? If it's equivalent to 1, then there's one bit in this 4-digit, right? If it's 2, again, because 2 is 1, 0, so you also have 1 digit, right? And this means like if you got a number 3, right, then it's 1, 1, right? So you have 2 bits as ones, right? So simply by plotting the result of this lookup table with what's the number that you are currently seeing, right? We don't have to compute like this, right? And if you think about this, this would need one addition at least, as well as one AND, right? So these 2 instructions are now combined with one addition plus one lookup to the table, right? In fact, this is doing 4, right? So significant reduction of dynamic instruction count, right? Because previously you need 1, 2, 3, 4 arithmetic instructions plus, well, actually 8 arithmetic instructions to calculate the same thing this 2 is going to do, right? So significant reduction. How about the second, lower branch misprediction rate? They have the same, right? Because the only difference is what's inside the iteration. The number of loops and when to terminate the loop, nothing being changed, right? So this 2, they are not true. So a lot of you pick C, so you think C also has a better CPI than B. Why do you think that way? Simply because of the performance is better? Okay, but let's run a demo and let's see if that's really true. So let's run the demo again. Well, let's grab the stats from the demo, right? So this is what we will see from A, B, C. So first of all, regarding the instruction count, the A was 33 something, B was 28 something. Now we see it's significantly reduced to 2 point, it's only like 1 of the third, right? So significant reduction. However, if you look at a CPI, it's actually worse, right? Again, don't forget, execution time is a combination between instruction count, CPI, and CT, right? And here, the only thing that we don't change is the CT. However, the CPI going up. Why? But why do we still get significant reduction in execution time? Just because we have reduced the instruction count very significantly. But can someone tell me why the CPI goes up?
We're using a table which won't fit in registers, so we use the stack for like memory,
Okay.
which means we'll have cache.
Okay. So a lot of you might think about like, okay, this small lookup table, right? It shouldn't take too much effort to access. And in fact, this is really small, so it fit in L1 cache. However, through your assignment, you should learn, even with L1 cache hit, how many cycles do we have to pay? 5 cycles, right? And that's the number that we keep using in the same class. I try to remind you, a memory access, even though it's 100% cache hit rate, 5 cycles. How fast is an arithmetic operation like shift or AND? 1 cycle. So you are trading this 1 cycle operation with 5 cycle operations, right? But simply because you have fewer amount of this 5 cycle operation. So that's why we didn't have the performance going down. But in fact, the CPI goes up because you are treating arithmetic operation as memory. So another way to look at this, right? So this is the data flow graph of C. We already learned it's one iteration per loop, right? But let's take a look. This is the instruction that will be generated in L6 and in the version D, right? So if you draw a data flow diagram, right, you will also figure out it's similar to the version A. However, notice that the significant difference between here and version A is that for this version, these 5 instructions represent 4 iterations, right? Previously, we have 5 instructions. For version A, it also has 5 instructions, but their 5 instruction is simply checking 1 bit. But here, we are checking 4 bits with these 4 instructions. So that's why this reduction of instruction count is super significant compared with the first implementation, version A, right? However, right, if you draw a data dependency graph, something you will figure out that is that the instruction 3 is indeed a memory operation. However, it seems like we are going to have a 5-cycle delay, right? But here is the internal issue that we can talk about, right? So the thing is, internally, the last time we talked about each x86 instruction will be rewritten as micro-ops, right? But internally, what happened here is we will translate that into 2 micro-ops. One is for address calculation, and the other is the real data access. And with that, the next iteration is not depending, the 3 of the last iteration is not really depending on the last iteration. And they can be somewhat parallelized. So that's why we still see it's about like 0.25 cycles per iteration because of that kind of optimization. However, even with that, the memory access itself still takes longer time to execute. So somewhat your performance is still bottlenecked by that. So that's why we see an increase in the CPI. Right? But the general idea here is that the performance of B is better is just because it has significantly lower amount of instructions. However, the lookup table is actually make each instruction on average takes longer time to execute. Right? So here you also learn a new trick, right? If you could have translate your complex computation into small lookup table, that's another way of accelerating your program. Right? All right. So for this question particularly, for B, C, and for 2 and 3, they are about the same. And for the first, that's true, but for the fourth, it's not true, right? So the only thing that is correct is actually 1. So this answer is actually 1, right? Most of you pick C, that's wrong. So, but the takeaway here is that, right, the second trick, right, we can potentially use a small lookup table to replace more expensive data dependency operations. Now, how about D and C? All right, let's take a look. Okay, so most of you think it's B, but you know, whenever there's one thing, let's try to think what's the one thing right that you have in mind. All right, let's take a look. So what do you guys think today? Okay, now more of you think the answer is C after discussion. So is D going to have fewer dynamic instruction count than C? No, why not? Say again? Okay, so this one has a while loop, so it will terminate earlier, so have fewer dynamic instruction count. And this one always runs for 16 times, regardless what's the number inside, right? So it doesn't have the chance saying that if you get a number like 1, right, this will terminate with just 1 iteration, but this still have to go through 16 iterations. How about the second one? Who has better misprediction rate? D, because it's pretty regular, right? How about the number of branch instructions? Same? C has fewer? Why? Because of early termination? How about the CPI? D? Why? But the data dependency is about the same, right? But you're thinking about the data dependency because of the X? Okay. So let's run a demo first, and then I will explain what's going on there. Okay, so let's take a look. This is the version A, B, C, D. They are now all in the same table. And for version A, okay, so let's take a look. For the version C, we already have significantly fewer instruction count. For this version, it has even fewer instruction count. Wait a moment, right? Some of us just saying that we missed the chance of early termination of the loop. But why this guy still have fewer instruction count? Right? Look at the CPI. It's slightly better than C, but not too much because of inside of the loop iteration. It's still doing the same thing. So the CPI doesn't change that much. So the CPI about the same. What really give us the performance difference is the instruction count, right? Now, final thing to check. What about the branch? How many branch instructions are there? For version D, we only get this amount of branch instructions. What's going on? Right? Some of you think we are going to have early termination of the loop. But in terms of that, this one actually has fewer. What's going on? So, there are things that also tells you, as a programmer, you really have to know how to write code. Because this is the thing. If I'm the compiler, I see you're always going to run the iteration for 16 times. What I'm going to do is that I'm going to unroll this loop. So effectively, the compiler would make this piece of code like this. So with this, a lot of other things that we can do, right? Like auto order scheduling, right? And eliminate all branches. And you might wonder why I'm still seeing the branch. Don't forget, outside of this function code, we still have another for loop control to make it, to call this function for 10 million times, right? So that's why you still see those around 10 million branch instructions. It's not coming from this function itself, it's actually coming from the outside. But inside this function, there is nothing branch. No branch at all, right? No, if you don't have branch, you won't have any misprediction. Agree? Right? So the best way to avoid a branch prediction problem is never trying to predict. Right? So sometimes, right, as a programmer, it's intuitive for you to minimize the operations that I need to do. But in fact, for this, be bold. More operation is actually going to give you better performance. Right? Very counterintuitive. But that's what computer architecture class can give you over those algorithm class. They will never tell you this is going to be better. They will tell you to write a while loop. But here I'm telling you, write in this way. And the reason is because in compiler optimization, as we mentioned earlier, if I cannot be 100% for sure, I won't do any optimization. Or I can only do limited optimization. But now, you have already told me you are going to start with 0, run to 16. It's guaranteed your code is always going to run 16 times. If I don't expand it for 16 times, I'm a stupid compiler. So any compiler would do this kind of loop unrolling if you turn on the optimization flag. Because it's 100% for sure you are going to run it for 16 times. Right? So here's the thing. Why is D better than C? Because the super crazy loop unrolling. And only the programmer can do that. Only the programmer can do that. Because you are the only one who knows if unroll it for 16 times is reasonable or not. Right? That's the power of you. Right? So for this, actually 3 are correct. Okay, so takeaways, right? Making your code more predictable is actually the way, right? Because compilers can confidently perform aggressive optimization if you give the compiler more hints. And branch predictor can be more accurate if your behavior is better, easier to predict. And cache miss rate can be really low if you know how to make your data access pattern more predictable. So these are the key. Now let's go back to this one. Why is E the slowest? The favorite thing of software engineer professors. Right? Why is so E? Why is it the worst? All right, let's take a look. So, definitely a question to discuss. So why don't you guys discuss with your friends and let us know what do you guys think? All right, let's take a look. After discussion, more of you think there are two. So, well, E has the most dynamic instruction count. Yes. Why? We have the same loop unrolling we can do. Why is it still have the most dynamic instruction count?
Because each switch pays what happens on compare and branch.
Each switch has a compare and branch, but it's still better than version A, right? How about the branch miss prediction rate? Is it going to be highest? Okay, so how about the data hazards? Okay, so here's the thing, right? Switch, it looks so elegant from programmer's perspective. Clearly see what's going on there. But what I want to tell you is that in reality, right, this is how we implement a switch. So you will figure out there is a table here, right? And this table is kind of like different in a way that you will see how its content is about is L5 minus L7. This L has nothing to do with the level in software company. And it simply specify the instruction to jump from the label of L7. But why are we doing this? Because what happened, right, in a code is you are going to do a comparison. And then you are going to use this jump to jump to a location. And how do we get the location? Is actually when you do the switch statement, you are going to perform an arithmetic operation to compare this, which is right here, and L, right, 15, right? So using that number, I perform a lookup in this table to see how long should I jump to from this position and jump to that instruction specifically. So this is actually in your code. You tell your code which instruction address should I jump to. So it turns out a branch instruction right now is not just a branch. It's a combination of a lookup table, which is a memory access now, plus a branch, right? And lookup table is already 5 cycles. And a branch itself, and this branch, where to jump to, can you predict, right? You have 16 possibilities, right? So that's why it is so slow, because first of all, you have more to predict, right? So like, for example, the traditional branch prediction is just a 2-class classifier. But now you are making this 2-class classification problem to become 16-class classification problem. You are making the problem even more complicated, right? So if we could take a look of, wait, what's going on? Don't think. Wait, is it the same? That's not the. Okay, let me do this. Why is it different? Okay, so let's go back to the table that I generated. So if you take a look at the table here, right? Because we still do things every 4 iterations, so the instruction count is actually better than A or even B. So this part, switch, still has its benefit. However, if you pay attention to the CPI, it's 1.5. And not only because we have translated each branch to be a data access, and also the branch misprediction rate is almost about like 0.2 times, is almost about 20%. So 1 out of 5 branches you are going to mispredict. This is a very high misprediction rate, right? And the main reason is just because it's a switch statement. So another lesson you should learn, right? Never use switch, right? It's terrible, right? Even though it looks elegant, but it's not a good idea. So now you might wonder, what's the best version to write in pop count? So through the software optimization, we already make the pop count going down from the most naive implementation, 22 seconds, to 3.7 seconds. But now I'm telling you, if you are a computer architect, you are familiar with the Intel architecture or AMD architecture, you know, and even this is also, and this instruction, because pop count is so important. So not only Intel and AMD has it, NVIDIA GPU also has it, and ARM processor also has it, but it's just in different name and format. So if you can use the intrinsic, which is pretty much mapped to an instruction in the x86, you can actually run even faster. So here is the version of code that you will write. It's pretty ugly, but just 1 line of code. This assembly instruction is going to give you the pop count result. And now I'm going to show you a demo on this. So let's run the pop count really quick. So if I do this pop count using the SSE version, it only takes, look, first of all, because now it's only like now think about this, right? Every iteration is just 1 line, 1 x86 assembly. So the instruction count is way lower than any others. The CPI is higher, but again, because right now each instruction becomes more complex, so the latency of that single instruction is longer, right? So this again lets you to think again. The performance is a synthetic result of the instruction count and the CPI. So simply looking at one is not representative enough for your performance, right? The miss rate goes up, but that's fine because our execution time is only 1.6 now, right? So here's the thing. Even though you have the best algorithm, if there is a hardware acceleration for that, forget about it, right? So a lot of you might think about, as a software programmer, we have many things to do, but in fact, sometimes the E people has more to contribute in accelerating. Okay, but here's the summary, right? If you look at all the pub count results we have, right? The execution time is the fastest if you leverage all the software effort is the D version, right? However, one thing to be aware. So here is a summary of how to program. And the last thing is that if there's a hardware feature supporting the desired computation, we should try it, right? Especially nowadays, every processor has a very wide set of instructions that they can accelerate a complex computation. Like in a modern x86 processor, they also have like this AMX instruction, which you can compute matrix multiplication in just one instruction, right? Okay, so now let's talk. So now, today, we have talked about performance optimization. However, there are always cases that we cannot make our code fully utilize the hardware. So for example, if you really have to run linked list for some reason, you are going to waste your hardware resource a lot. Like this slot is completely wasted in your processor. And even for the pub count, right? If you look at the instruction level parallelism, which is the reverse of your CPI, you will figure out that even for the best CPI that we can achieve, we still can only use 4 out of the 5 LUs or memory units that so we have 12 issue widths, but the best is only used at 4, right? And if you do hardware acceleration, you only use 2.6. So what does that mean is that most of the time, you cannot fully utilize the functional units that you have in the processor, right? So here's another source, right? So this idea is called simultaneous multi-threading. So the concept of simultaneous multi-threading is pretty much like this. If we always have code that we always have to run code that we cannot fulfill all the hardware units, what if we tweak our hardware in a way that we can invite another thread to come in and share the same pipeline whenever there are free functional units? So what does that mean is that right now, let's say, okay, we have UC San Diego campus, right? How many of you go to gym every day? Yeah, I saw you one time. Who else? Right? So here's the thing, we have a gym that's designed for like 47,000 students, but most of the time only Alex going to the gym, right? So what does that mean? You have a lot of free bandwidth, right? So turns out what UC San Diego doing is that we offer the so-called community pass to people who live around this La Jolla area to share the resource that UCSD provided. So what happened in modern processor is that what if we open up the functional units for other threads or other processes that I'm currently not scheduled on this processor to share the resource so that both of us can make progress and we can fully utilize the hardware. So that's the concept of simultaneous multi-threading. So if you want to do simultaneous multi-threading, turns out that it requires you have an environment that is multi-programmed. What does that mean by multi-programmed? It means that in your operating system, in your program, you may have multiple applications that are run in parallel or a single application that spawns multiple threads or create multiple processes that's run concurrently on the same computer. This is the common case now, right? Like look at your iPhone, right? I typically don't believe people just run one app at a time, right? So this is everywhere. And there are several different abstractions that you will learn in operating system trying to create this kind of abstractions of running parallel computation in one single machine, right? So this is a common scenario that we have right now. And simultaneous multi-threading design the hardware to run multiple programs on a single processor pipeline. So this idea is actually invented by Dean Townsend. He is currently a professor in this department, and he is actually my advisor. And the other one here is Steven Swanson, the new department chair. So you know why am I teaching here, right? No, I'm just kidding. So, but the thing is that this idea of simultaneous multi-threading, they exploit the thread level parallelism on top of the instruction level parallelism that we have in a superscalar processor. So here's the concept, right? This is the original processor you have. You have one register, you have one set of register, you have L1, L2 cache, and the last level cache. And traditionally, each time you can only run one application at a time. But what happened in simultaneous multi-threading is that they create an illusion. They try to cheat, to be honest. They try to cheat the operating system saying that I'm available, try to run me, right? So it's pretty much like dating apps. Some people saying that they are available, but they are not available. But anyway, so this is like, okay, so traditionally, each processor should only have one program counter with one core ID. But with simultaneous multi-threading, we are actually creating another program counter so that you can track the progress of another program and another core ID, so the operating system will be full saying that, oh, I have two processors now. So I can schedule two programs on there. And internally, because you schedule two programs on there, so you are able to schedule multiple applications on the same processor. So that's the concept of simultaneous multi-threading. So as you can hear, all you need to do is reusing the whole superscalar processor, just add one more program counter and reveal more core ID to the operating system, right? So that's a pretty good deal, right? So all you need to do is just making a duplication of the program counter, and you can enjoy the benefit. But is it good? Is it always good? All right, let's take a look. So whenever you guys don't know the answer, you will pick C. So why don't you guys like talk to each other with regard to the two that you have in mind with others?
I presume what happens is that with the SLT is that multiple predictions are ran at the same time. But what if that happens?
I thought three because if even it's in the sense, it can have better. It's still doing more things. It's still like it's still doing other jobs. Even the system job that I approved. It's better to do something hands-on than not do nothing.
All right, let's take a look. So, after discussion, something changed, right? So that's why we need it. So how about the first one? Would SMT make processor with deep pipelines more tolerable to mispredicted branch? Yes or no? Yes, why? You're not sure.
What does deep pipeline mean?
Like many pipeline stages.
So like a large critical path or
Like a very long pipeline, like the processor we have right now has like 30-ish stages. So when you have a mispredicted branch, you have to wait for 30 cycles, right? So would SMT make it better? Yes, why?
Because if you mispredicted something, you can you're not just using that thread, you're also using that.
Right. So here's the thing, right? If I'm mispredicting, if I'm stalling for something, I can basically fetch instructions from another thread, right? So at least someone is making more progress, right? So the first one is true. So in that perspective, do you think the third one is also true? Yeah, right? Now, how about the second one? No, why not? Okay, so let's ask Alec, right? If there are a lot of people in the gym, would you have to pay longer time to finish your workout? No, why not? Yeah. Right, why? Because you have to wait for specific machine, specific space, specific equipment, right? So if you have more threads sharing the same hardware, it's actually hurting your single thread performance because right now you have to wait for the functional units more often time, right? So the second one is actually false. How about the fourth one? Not true? True? True, right? Because again, it's about sharing, right? So it could have higher misprediction rate. And so in fact, 2, right? So in fact, oh, so sorry, three are correct because it's higher misprediction rate, right? So in fact, even though with some drawbacks, but the benefits is outweighing, and because the hardware cost is really small. So if you pay attention to modern processors, whenever you see they say threads per core is 2 or more, it means that it's simultaneous multi-threading enabled. And if you have an Intel processor, AMD processor, it's pretty much like you're going to have those simultaneous multi-threading cores. So now, before we finish the lecture today, a few things I want to talk about. First of all, assignment 4 due this upcoming Sunday. Very last reading quiz due next Tuesday, and then we are ready for final. Check your latest grade on this website. And for some reason, I saw a lot of you, your browser doesn't really refresh it automatically. So check the timestamp of the source data that I have regarding your grade. So make sure it is August the 27th, and it should reflect the participation grade up to yesterday, as well as all the reading quizzes up to yesterday, as well as your midterm grades. All right. Other than that, enjoy the rest of the day. I will see you tomorrow.